Hello, everyone. Welcome to the 17th webinar in the Joint Tran-SET webinar series, which will cover different projects related to warm mix asphalt to improve pavement sustainability from three quite different perspectives. Today, we're privileged to have three transportation experts presenting in this webinar. We will have three 15 to 20-minute presentations. First, Dr. Zahid Hussain will discuss the feasibility assessment of warm mix asphalt in Arkansas. After that, Dr. Luai Mohammed will present on long-term field performance of warm mix asphalt in Louisiana. Finally, Dr. Devakanta Mishra will present on warm mix asphalt, a logical choice in our drive towards net zero emissions. We will save questions until the end of the three presentations for a 15-minute group Q&A. You can type your questions anytime throughout the session. Without further ado, I will introduce our first speaker, Dr. Zahid Hussain. Dr. Hussain is an associate professor of civil engineering at Arkansas State University. He has over 15 years of experience in developing sustainable construction materials through mechanistic and surface science techniques. He has authored over 100 peer-reviewed articles and served as an editor member of several scientific boards. Furthermore, he's a registered professional engineer in the state of Arkansas. Dr. Hussain, I will turn it over to you now. Hello? Dr. Hussain?
It shows he's on mute.
I don't know if his connection. Yeah, I see him here. Okay, maybe we can start with the second presentation. We can start. Dr. Luai, would you be ready right now to start?
I am ready, yeah.
Okay, let's start with your presentation, please, until Dr. Or there's Dr. Zahid. Dr. Zahid, can you hear me? Hello?
I think there might be an internet issues.
Yeah, then let's go ahead with your presentation, Dr. Mohammed, until Dr. Hussain fixes his problem, and then we can jump to go to his presentation. Okay. Okay.
Okay.
Yeah. Okay. I will introduce you now. Okay. Perfect. Okay. Dr. Mohammed is a professor of civil and environmental engineering and holder of the Irma Louise Rush Stewart Endowed Professorship and Transportation Faculty Group Coordinator at Louisiana State University. He's also an award-winning professional engineer, a Transportation Research Board Emeritus member, and an elected fellow of the American Society of Civil Engineers. Dr. Mohammed serves as the Director of the Engineering Materials Characterization and Research Facility at the Louisiana Transportation and Research Center. He teaches and conducts research in the areas of highway construction materials, pavement engineering, accelerated pavement testing, advanced material characterization and modeling, and infrastructure resiliency and sustainability. Dr. Mohammed, I will turn it over to you now. Sure.
Okay, can you see my slides?
Yes.
All right, thank you, Daniel. And all right, the topic that I'm going to cover today is basically related to warm mix asphalt And a lot of times what one does is you build a road with various different technologies, and then the question is, did it work or did it not? You do a lot of things in the lab, but the question is, once you put them in the field, what's going to happen? And so this study basically attempt to offer an answer to that. So what I will attempt to do is to talk to you about background, objective, how did we do the research and the experiments that we have conducted, as well as results and some key takeaways from this research. So asphalt mixture has component materials typically that are asphalt binder and aggregates. And more often than not, additives are included in the mixture in order to improve performance and durability. And durability is a key topic, particularly at the national and the federal level, specifically for those who are familiar with the Code of Federal Regulation, where it says that pavements shall be designed to accommodate current and predicted traffic needs in a safe and durable and cost manner. So what are these things that can improve durability? So first, let's know what is a durable pavement. It's one that typically would resist permanent deformation, fatigue cracking, low temperature cracking, moisture damage, raveling, durability, among other things. So these are some major distresses. The additives that are typically added into an asphalt mixtures, they fall into a category. And these are the list of categories that one can look at. And they range from a filler, extenders, polymers, fibers, oxidant, antioxidant, hydrocarbons, anti-strip additives, waste material, and finally you see the warm mix asphalt. And this is our topic because it can improve durability. And one of the characteristics these additives have is that they can reduce mixing, compaction, temperature, which eventually lead to improved density. And further, it participates in the development of sustainable activities. So when one talks about sustainable technologies in flexible pavements, they could come of different types. And these are two categories. One can be sustainable by the type of material included in the asphalt mixtures, and they're listed right here. Or they can be sustainable by the way they're built. And there are many different ways. And this is what we're talking about today, is the practice of construction where one can include additives. And this particular additives is the WMA. And they come on to a different types. It could be a chemical, organic, water-based, and also on an equipment variation, such as the Aztec double barrel type of plant. And this slide shows you a recent survey that was done in 2019 by the National Asphalt Pavement Association, where it cites there were about 157 million tons produced in this country of asphalt mixtures. And you could see that a significant amount of that, about 80 million tons, included a WMA technology. So we are making headways into including those additives into asphalt mixtures from the time where it was introduced about 10, 15 years ago. And so, and also in that particular study showed that the typically 10 degrees F is used to reduce temperature, and most WMA mixtures use plant foaming because you don't have to add anything. And the second thing that is used is to include some additives. So the advantage then of using a WMA additives are listed in here, and it includes basically it allows you to reduce the mixing and placement temperature. What that basically means that then it can improve the workability of the asphalt binder, and also you can establish a longer paving period. It can reduce energy consumption. It can participate in the reduction of emission of greenhouse gases. And from a material standpoint, it can allow you to use an increased RAP content. And you can see that all these things can be incorporated into the development of a framework for sustainable development. And in terms of performance, then we know the advantages. Well, what do they do? Is there an established track? And at the national level, there was an NCHRP 949A, and that was one of the most extensive look at WMA performance in the field. And some of the finding in there is that typically you would conclude that WMA performed as well as conventional asphalt mixtures relative to distresses such as cracking and permanent deformation. So that led us to the objective of the current work that is sponsored by our DOT, which says that we are going to look at field performance of WMA technology that were built several years ago. How did they do? And at the same time, when we built them, we conducted several mechanical tests in the laboratory to see that which of those tests can correctly rank what is observed in the field. And to achieve this objective, we looked out at various sites around the state, north, south, east, and on the west side. And those 4 field rehabilitation projects, they had about 12 test sections. And on those sites, we were able to do a data mining from our pavement management system, which allow us to compute the performances of these materials. And our PMS system, we can look at the indicators themselves of distresses, then develop indices based on severity, and then look at the overall performance combined on those various distresses. And so this slide shows you the structures that were considered into these field projects. And we had one on LA 3121. It's about 8 years old, and that is the traffic level. And this pavement is the only flexible one. The remaining 3 structures are composite ones. We had US 61, US 171, and US 90. And you could see that in each one of those sections, there was a companion conventional mixture. So one can make a direct comparison to the ones that includes the WMA additives, which could be of several types. Each section had different additives. For example, 3121 had Evotherm. The 61 had Sasobit and foaming. The 171 had Ready-Set and foaming. And the US 90 had Evotherm. And some of those sites also included an increased trap content from 15 to 30% in 3121 and route US 61. What you see in here is that some of them were built on composite structure. So that might yield some issues, as you could see in the result, because it's not really a material issue, because if you have a problem underneath in the composite, which is the PCC or the cement treated base, that's going to reflect on the surface performance. So keep that in mind. If we see anomalies, that's not necessarily due to the additives, it's probably due to something underneath. So in the field experiment then, we have the information that we get from our DOT, and because it does a survey of the highway network every 2 years, and it collects distresses and it classifies them based on geometry as well as severity. And you see the list of the different distresses in here. And it also collects the stresses. And this process is very tedious. It's got a lot of data mining because you got to separate the distresses. It's collected every 1/10 of a mile. And also we wanted to separate the, for example, the load associated cracking versus non-load associated, meaning the edge cracking and the longitudinal joints, because these are not really related to the performance of WMA. And then once those data were collected, then we looked at the indices to analyze the data, specifically the performance indicators, the performance indices, where it looks at the distress and the severity. And this is the equation that our DOT has developed based on a deduct depending on the severity. So if there are no severity, then the deduct basically is 0. So it's a perfect condition. And then we looked at then combining all the distresses together, the indicators and the indices, to compute a PCI that looks at the overall condition of the pavement. So it gave us a lot of tools in terms of field assessment. Now we go back to the laboratory because the objective was, is there a lab test that can rank those distresses at high temperature, intermediate temperature specifically? So we looked at that time when the study started, we had an LWT for high temperature, flow number for high temperature as well. And we looked at 2 tests for intermediate temperature cracking, which is SCB as per ASTM 8044 and the dissipated creep strain energy test. And so now we've got all this information. Let's look at snapshot of some of those results. And there is a report on this for those of you who are interested, as well as a TRB paper. And so what you see in here, first of all, we looked at the field rut depth for all those various treatments. And if you just have a snapshot look at it, you can quickly state that typically the WMA mixture at least has performed similarly or slightly better than the mixtures that has a conventional one. And those A's, basically, these are the statistical grouping. So they are either statistically similar or statistically better or statistically worse. If you look at, for example, this project 3121, we increased trap content. Intuitively, you would think that basically rut depth should decrease. However, this shows that even though it did not decrease, it had a slight increase. And this is one of those things that I was saying earlier. This probably could be due to what's underneath that WMA. And this is something we're further investigating right now. And then if you look at the projects on US 61 right here, and this is what you see basically is that the had a slightly lower rutting as compared to the conventional one. And similarly, one can look at the 171 and the US 190. WMA did well in terms of field rutting. So at least the technology seems to be promising. The next thing that is in here is the roughness of the pavement as documented by IRI. And in these particular variations of routes, one can see that, again, in general, the WMA mixtures had at least statistically similar to the conventional mixtures. This guy right here on the LA 3121, you see that higher rep content showed slightly rougher, because we did see that it's got a little bit rutting, so you would expect that to be rougher. And in this case in here, as well as you see in the US 90, is slightly higher, but the key in here is that they are statistically similar. They are not significantly different, except for the US 61 project right here. Then we move on into intermediate temperature activities, and specifically, we're looking at the longitudinal wheel path cracking. And what you see in here is that the mixture that has 30% RAP had significant increase in cracking. These mixtures that on US 171 is that this is a conventional mixture. You look at the one that is the WMA, it has a significant decrease in those that has a WMA. Further, if you look at the effect of that 30% RAP, it does show that a slight increase, however, it is statistically similar. Now, once again, you see that there are effects of the underneath layer that may cause some results that does not match what's expected. Looking at transverse cracking in this particular slide from field performance, and one would observe in here is that you see that the HMA and the WMA, most of them were statistically similar. They might be slightly higher in number, but they were statistically similar. It's interesting that the 30% RAP had slightly lower transverse cracking. And again, this could be issues related to what's going on underneath. Right here, you see that what's expected in the US 90 is that the 15% RAP mixture did extremely well in crack resistant as compared to the counterpart HMA mixture. Now, having said all these things, now it's time to combine them all together. See, how do these compare? So, and that's looking at a PCI. And looking at the PCI, then what one observes in these combination is that typically the WMA mixtures did at least as good as their counterpart HMA or slightly better. What you see in here is that and in some cases that this particular mixture that has a 30% RAP did show a lower PCI as compared to these other mixtures based on these other distresses that were compiled in an earlier measurements. Similarly, in these other sites, US 61 shows similar in these particular systems right here. Now, some of them had slight variation, not only in the content of the additives, but also aggregate types. So this could be a contributor as well. When you deal with field condition, sometimes that's what you get. And looking at US 171, that's our best controlled experiment in the US 171. And you see that the effect of these various additives and the effect of RAP, and as well as the one on the US 190 system. So now I showed you a lot of results, which is basically a snapshot. It's not every type of distress. It's not every type of indicator. So then what we wanted to look at, say, okay, let's look at the grouping where WMA is either equal or better in all of those 34 various pairs that we looked at in terms of a indicator in the performance indicator, the performance indices, and PCI. And that kind of give you a bigger picture. And what you see in here is that in those mixtures where WMA was at least equal in performance or better than hot mix asphalt, we had 71% of those pairs of those 34 systems that we compared. And in terms of performance indices, the similar statement increased to 73%. And in the PCI world, then it increased to 75%. So that kind of gives you an indication of how did WMI technology did in the field in terms of measurement. So that's kind of the first objective, what we looked at. The second objective was, well, how did these laboratory tests compare into these measurements? So these are the 4 sites. This is the each section in each site. And you would see that this is the high temperature laboratory test, another high temperature laboratory test, which is LWT and a flow number. And the last column is the field measurement. And that kind of gives you a snapshot of, do they have a similar ranking or do they have a different ranking? And you could see that in this cases, some of them have a slight different ranking than the one that is measured on the field. In terms of intermediate temperature, then, we looked at the SCB-JC versus the dissipated creep strain energy versus longitudinal wheel path tracking. And you see that JC was able to correctly rank those mixtures. Again, this is ranking those mixtures for those test sections as similar to the field. And that's the bottom line, is that can the laboratory test rank what you are going to expect in the field? And you see that in here, this section was not correctly ranked. This section was not correctly ranked. And then if we look at the same intermediate temperature cracking, you see that fatigue cracking was able to correctly rank those by SCB-JC as opposed to the dissipated creep strain energy, which was not able to. So then to put this in numbers, then what all this tended to say is that the ability of a laboratory test to correctly rank mixtures were 100% in terms of LWT and 87% in terms of SCB-JC for those test sites that we evaluate. So that kind of always gives you an idea, is the laboratory test that is developed and used relate to field performance. So these are some of the technical data that can offer you a baseline for whatever mechanical test that you want to use. So the key takeaway then, in summary, for this particular presentation is that what we observed is that WMA test section did well when compared to HMA sections. And specifically, those WMA sections showed significantly lower resistance to cracking as compared to the control mixture. In terms of laboratory parameter, LWT is a good indicator of high temperature, as specified by AASHTO T324. SCB-JC parameter, as specified by ASTM D8044, it's another good indicator for field cracking for the sites that we have measured and the tests that we have done. And in some additional observation we looked at, we saw an increased ROP content resulted in lower LWT rod depth in the WMA section. And this is again due to possibly the layer underneath the top. So it's more of a structural issue rather than a material issue. And on 321 site, as well as 61, the WMA section basically showed lower cracking than counterpart in HMA section. And more importantly, all of them right now, they are below the rod depth of 12.5 field rutting that triggers an action. This is our value where it tells our DOTD it's time to do a rehabilitation. So far up to 8-10 years, and we expect to see whole more, that they are all doing fine. And also increased ROP content result in an increased fatigue cracking for those sites that we have measured. In acknowledgement and order for a lot of the individuals who are involved in the development of the data and the presentations, and I am just the messenger. And this is basically Dr. Moses of LTRC, a graduate student, DOTD Pavement Research Group staff, as well as the DOTD Pavement Management section. So we have a lot of people that helped us get to this point. And with that, thank you for listening.
Okay, perfect. Thank you very much, Dr. Mohammed. That was excellent. Now, I will introduce our previous presenter, Dr. Zahid Hossain. I will reintroduce him. Let me share my screen with his presentation on feasibility assessment of Wmi Asphalt in Arkansas. Okay. Dr. Hossain is an associate professor of civil engineering at Arkansas State University. He has over 15 years of experience in developing sustainable construction materials through mechanistic and surface science techniques. He has authored over 100 peer-reviewed articles and served as an editor member of several scientific boards. Furthermore, he's a registered professional engineer in the state of Arkansas. Dr. Hossain, I will turn it over to you now. It's on mute, Dr. Hossain.
Sorry, Ayan, could you share your presentation slide?
Yes, I've shared it.
Okay. Can everyone see the slide now? The title is Feasibility of Warm Mix Asphalt in Arkansas.
We are looking at Dr. Luai's presentation still. I think Dr. Luai might need to unshare first. Okay. Now we can see it.
Okay. Great. Thank you. Again, I apologize for that disruption. So this, as part of this project, we did a kind of a proof of concept study. As you know that many states, they adopted or implemented some of the WMI technologies. They have the field work, field projects, but for Arkansas, we are kind of behind. And based on our literature review and everything available in the public domain, we did not see much literature. In fact, not much on the additive based warm mix asphalt. Most of the warm mix technology has been followed here in Arkansas is foam based. So we looked into additive based warm mix asphalt technology as part of the project. Next slide. Could you move to the next slide? Thank you. As we know that warm mix asphalt technology, it can reduce the temperature significantly. In the previous literature, we have found that it can reduce up to 55 degrees Celsius temperature. And you know, all of you pretty much know about like the benefits of warm mix asphalt, and Dr. Louis Mohammed elaborated some of the items there. So basically it reduces the energy consumption. It also hazardous element emission. So that will be better. But again, we did not see mass additive based warm mix asphalt technology. I used Oklahoma. I am from Oklahoma. That is my type. Actually, I'm talking about Arkansas. So we tried 4 different types of additive based technology in the laboratory. Mostly we focused on the asphalt binder. So you wanted to see some data so that we can get more confident as a proof of concept, and then we can further probably move on to a mixture and field study. Next slide, Ion. previous literature, we know that warm-mix asphalt, it's not new anymore. In late 90s, that is the time when it started in Germany. And the United States, like early 2000s, that is where the warm-mix asphalt was tried. And the first projects were from NCAT, and they used Thasobit, Evotherm, Asphalt, and there was significant reduction of compaction as well as mixing temperature, and also that preliminary of the first those first warm-mix asphalt technology projects. They found also there is a possible grade change, performance grade change, if these additives are used. And then there are other researches were done, but I just mentioned few. That is from my own research group that is at the University of Oklahoma when I was first in 2008. That is Dr. Wasuddin and his group started, and then we continued. So there are like 3 citations I have provided. Those are when I was in Oklahoma, and we did for Oklahoma. So basically, what we found that the Thasobit, mostly focused on Thasobit and Asphalt. Again, that was laboratory-based binder study. Thasobit significantly reduced, not significantly, but it reduced the viscosity, but Asphalt did not. So one of the reasons is that Asphalt is not meant to be done in the laboratory. It is in the field, in the mixing process. So that's why it is hard to simulate Asphalt in the laboratory. And also found that Thasobit improved the rotting performance in terms of rotting factor. And then the mixing temperature, it was like about 9 degrees Celsius reduction with 1.5% of Thasobit. And if we use more Thasobit, then it was kind of detriment temperature cracking. And Adbera, we did not, again, we could not simulate the field, so we got some kind of negative results. So that is, I would say that that's the shortcomings of our laboratory testing. And then Bennett and his research group studied Rpfo and Evotherm 3Z, and they found that for 76 minus 22 binder, it was they found it was coated easily with those additives, and the mixing temperature was reduced significantly. So like about 25 degrees Fahrenheit reduction of mixing temperature. And Kasim et al., they did a study, Thasobit, Evotherm, and Rpfo. Ramada in 2020 used Rpfo and also reported improved kind of moisture resistance. Next slide, Adam. So primary objectives of our study was to see how much reduction in mixing and compaction temperature would be. And then also we looked into like if there is a change in binder grade. So not only the mechanistic or rheological properties, we looked into chemical properties. Mostly we focused on Sarah fraction and FTIR test that we have done. Also we did pH test, acidity measurement. And then other thing we did surface science approach. We did surface free energy calculation, and then from there we looked into the compatibility between different types of aggregates and the binder to see which one is more stripping resistant. Next. Here is a snapshot of our project plan. So in short, we did the literature review. Then after sample preparation, we tested asphalt binder, unaged, Rpfo aged, PAB aging after PAB aging. And then we did super PEP test as well as some chemical selected chemical test. And also we did some very limited, I would not call it mixture, but it is kind of a loose mix test. So we did Texas boiling test to see what kind of retention of binder would be with different kind of aggregate. And then we came up some kind of like concluding statements based on, again, limited study. Next. All right, so the materials that we used, three performance-based binders, PZ64 minus 22, 70 minus 22, 76 minus 22. Those are the binders, those are used in Arkansas. They are approved by the Arkansas DOT. And we designated them binder B1, B2, and B3. But we tested all three binders from two different sources. One is from airgun, another one is from Marathon. Typically, Airgun uses a Canadian crude, and Marathon they use mostly it is Arabian crude. So that is kind of like we looking to see if crude source has kind of any influence, and actually it does. From other study we found that, but at least like we tried from two different sources. And also we considered four types of aggregate: the sandstone from Apex Central, Van Buren, and gravel from Capital Quarries, Pocahontas, Arkansas, and limestone, that is White River from Ford, Arkansas, and dolomite from Capital Quarries in Pocahontas, Arkansas as well. And some general characteristics are provided on the right side. So, but I'm not going to in detail, but those are based on the literature. We did not do any kind of like chemical test of the aggregate. Next slide. Okay, and then we tried four types of additives. So those are Sassobit, Asphalt, and that is actually Adbera 401 PS, Rediset, then the other one is Evotherm. And we have listed like from MSDS data file, we looked into like what are kind of color, appearance, and chemical composition. And there are some pictorial views of those additives as well. And briefly, it is Sassobit is a Fischer-Tropsch hard. It is wax kind of materials, long carbon chain. And then Asphalt, that is kind of zeolite. It has about 20% of water. And then Rediset, so that is kind of, yeah, it is alkylated fatty polymers, the kind of chemicals, and C4, H10O3, combination of other materials. And Evotherm, that is modified tall oil fatty acids. And the recommended doses, these are the recommended doses. The Sassobit is like 0.8 to 3%. That is the by weight of the binder. And then Asphalt, it is 0.05 to 0.3%. So that is by the weight of the mixture. That is different from by weight of the binder. But the other two, Rediset, Evotherm, they are by the weight of the binder. So Rediset recommended is 0.3 to 1%, and Evotherm is 0.25 to 0.5%. As you can see that there is, the scope was very, yeah, it is expanded. So what we did, we did only the viscosity test, and from there we kind of, and from literature, we kind of determined what would be that optimum doses. And then we tried with that optimum doses of each of the additives and looked into other properties. Next slide. The sample nomenclature. So basically we did, so it is by 64 minus 22, that is noted as B1, and source it is S1. So you can see that second column that shows the additive, and the third column, so that is from source one, and the binder B1, B2, B3. Again, B1 is 64 minus 22. Then B2 is 70 minus 22, and B3 is 76 minus 22. And then we have A0, A1, A2, A3, A4. So A0 is there is no additive, and then Sassobit 1.5%, that is A1, Adbera it is A2, Evotherm A3, Rediset A4. The fourth column, so that is from the other source, from PQ Corporation, from source 2. Next slide. The methodology, so that is, we just showed the pictorial views of different test methods. So we were showing like how the sample was blended, and then we did hand blending, manual blending for this project. For other projects, we do high shear mixture, but this one hand blending was kind of convenient for us, easy to control. Then we did penetration test. Penetration test, this is kind of test like some of you research for your research work, maybe you do not do it anymore, but this is one of the tests. Still, Arkansas DOT uses that. From all of our project that Arkansas DOT sponsors, we do now include penetration test because they are familiar with this test. They still run this test. And then other super pave test, rotational viscometer, rolling thin film oven, pressurizing vessel, then degassing oven to take the excess air out, and then dynamic shear rheometer. And then it was showing like some plates, like 25mm plate as well as 8mm plate, and the bending beam rheometer. Actually, we did not have the bending rheometer, so we got help from Purdue University. Dr. Haddock, he helped us to do this test. And then we did SAR analysis. We are capable of doing SAR analysis, but because of the COVID and other things, it was kind of taking too much time. And so we got help from Paragon Testing. So they did the SAR analysis for us. Dr. Cordin Daranga and Dr. Galen Baumgartner help us to do this SAR analysis. And then you can see that there is a snapshot of contact angle analyzer that is to run the Cecil drop test, and then some snapshots of a Texas boiling test followed by the acid number. And then give you some of the test results. Next slide. Rotational viscometer test. So that is what we have found, that viscosity, mostly Sasovit, that reduce the viscosity for all binders. And Adbera, it is kind of, as you can say, it's a 20% water. What is the purpose of creating the volume expansion? Or but we could not do that. So that's why most of the time we found that viscosity increased. So that is again a laboratory issue. It's there. And Evotherm and Sasovit kind of mixed effects on viscosity. Some of them decreased. That is for source 1 binder. And the next slide, so that is for source 2 binders. So we have source 2 binder. We see some little bit of different scenario. That time we found that both all Sasovit, Evotherm, and Rpfo, all three of them reduced viscosities for all binders except Adbera. Then the next slide is showing like a typical curve how we found the mixing and compaction temperature. So mixing, as you know, that we know viscosity 170 millipascal second plus minus 20. So that's why you had the upper bound 190 and the lower bound it is 150. That is my mixing viscosity. And then compaction, that was 280 plus minus 30. So that's why we got from viscosity would be 250 to 310. And then from there we found the mixing and compaction temperature range. In the next slide, yeah, would you mind please mute your microphone because I am hearing a lot of noise. Thank you.
But let me know. So if not, I can. If I don't.
Then the production temperature. So that this slide it shows the production temperatures. Production temperature in short for the source 2 binder, source 1 binder, we did not find that much of reduction, and so that is like Sasovit, Evotherm, Rpfo, mixing temperature reduced to 1 to 5 degrees Celsius temperature, and then Adbera mostly increased the production temperature because the viscosity increased. Source 2 binder, we found little more. That is kind of like 2 to 4%. 2 to 4 degrees Celsius, and Adbera it is also increased. Next slide, it shows penetration test. So the penetration test, again, left side, that is for source on binder, right side is for source to binder. What we have found that Sassobit mostly stiffen the binder. And that was from our previous study. You also found that that kind of increase, Sassobit stiffens the binder. And Evotherm Ready-Set, it has kind of like, it is sometimes it kind of stiffens, sometimes it kind of like is bit, but not much significant effect. So mostly on the make it little bit, this kind of about the same, I would say. For some of them, it's a little bit increase, some of them decrease, so not much significant. And then dynamic shear rheometer test, as expected, like we found that Sassobit, because it has stiffened the binder, so it increased the rotting factor. So that means it is going to decrease the rot potential expected. And then Ready-Set, because it makes the binder a little softer. So that's a little bit of lower rotting factor. And Evotherm mostly increased that, again, it reduced the rotting factor a little bit. So that is from source 1 and source 2. So that is Sassobit always decrease that rot potential. And you can see that Aggregate decreased in the Ready-Set. We found that most of the time it increased the rotting potential, and Evotherm mostly increased it again. And in terms of fatigue performance, we did test at intermediate temperature. So that is where we found that Sassobit and Aggregate that actually increase the rotting factors because it makes the binder stiffer. On the other hand, Ready-Set and Evotherm, we found that rotting factor reduction. So, so that indicates like there would be more rotting resistance if we modify by Ready-Set or Evotherm. Next, on the from the bending beam rheometer test, we could not find significant influence or kind of detrimental to low performance grade, especially from S value, stiffness value. It made the binders even softer, all of them, especially. But one case like Sassobit, one thing we found that 1.5% is still, it kind of, the M value was kind of in the borderline. It was even lower than 0.300. And that is kind of like, yeah, even from our previous studies, we also find that 1.5%, it is kind of reduces that M value. So that is for Sassobit, that's kind of detrimental. But Evotherm and Ready-Set, they make the binder softer. So that is kind of in a good, sense that is better. But BBR test result did not have any significant kind of effect. Next, we're going to talk about that multiple stress creep recovery. So from there, we found that Sassobit increased that percent recovery, whereas the other binder, other additives, Aggregate, Evotherm, and Ready-Set, that kind of reduced that percent recovery for a couple of binders, 64 minus 22 and 70 minus 22. And also some of them, Aggregate and Ready-Set, mostly changed the binder grade, MSTR grade, without adding additives. It was like extreme. And then we came to very heavy. Let's go to our conclusion. Go to the conclusion. I'm running out of time. Yeah, conclusion slide. Ayan. Yeah, move on, conclusion. The concluding statement. Yeah, so that is like we found that the viscosity reduction, that was that was most, it was Ready-Set, followed by Sassobit. And temperature, it did not up to only 5 degrees Celsius. Higher reduction was for Sassobit and Ready-Set. And in terms of thermal cracking, Ready-Set performed better. And then chemical analysis, we did not go in details, but what we found that Sassobit may increase the moisture susceptibility due to lower surface free energy. And Texas boiling tests support that Evotherm and Rediset showed better retention of asphalt binder, but Sassobit and Adbera had poor reduction. Next slide, some of the things I would like to mention. In terms of laboratory, we had consulted actually the manufacturer. They gave some kind of ideas, but because of the time, we could not do that. For example, Rtfo aging, probably, yeah, we should have done at lower temperature than Astro procedure. So that is one thing that we can do in the future. Then from Ingenuity, we are notified, or we are told, like the effect of Evotherm would be, we can see when we have multiple rounds of PAB aging. So that is something we did not do as part of this project. And Adbera is the volume expansion we could not simulate in the lab. So those are kind of, I would say, that shortcomings of this project. And this was a 1-year project. And in the future, yeah, of course, you have to do some mixture testing and probably some kind of a field testing. And I need to acknowledge many people and organizations. So I have in the next slide, I listed pretty much all, most of them in the acknowledgement section. So all the financial support, industry partners, and then binder suppliers, aggregate suppliers, additive suppliers, Paragon testing, and there are several individuals I listed. Thank you all. Sorry, I took more than allocated time.
Fine. Thank you very much, Dr. Hossein. That was really interesting. Now I will introduce our last presenter, Dr. Mishra. A second. Okay. Dr. Mishra is an associate professor in the School of Civil and Environmental Engineering at Oklahoma State University, where he teaches courses in the area of geotechnical engineering, pavement engineering, and railroad engineering. He joined OSU in August 2019 after spending 5 years as an assistant professor in the civil engineering department at Boise State University. Prior to that, he completed his PhD and postdoctoral work at the University of Illinois at Urbana-Champaign. Deb's research interests are in the areas of advanced laboratory characterization of infrastructure materials, instrumentation performance monitoring, and numerical model of civil engineering infrastructure, and application of machine learning and artificial intelligence for network-level pavement railroad condition assessments. Dr. Mishra, I will turn it over to you now.
Okay. I think I'm unmuted. All right. Daniel, do you see my screen?
Yes.
All right. Hello, everybody. Good afternoon. My name is Deb Mishra. First of all, thanks to Tran-SET for this opportunity. And I'm going to present a little bit on one of our ongoing projects. And the title of my presentation is What Makes Asphalt a Logical Choice in Our Drive Towards Net Zero Emissions. Okay. So sustainability or sustainable alternatives, that's basically the future. If you look at the, this is a screenshot of the executive order from the president's desk on December 8, 2021, and several sections talk about, net zero emissions from federal procurement, climate resilient infrastructure, climate and sustainability focused federal workforce. In the sustainable acquisition procurement, there is a section that calls about, refurbished or recycled materials, maximizing environmental benefits, cost savings through full life cycle cost methodologies, and stuff like that. So essentially, as a community or a society, we will be moving towards, or we are moving towards, looking for sustainable alternatives. And in the asphalt materials and pavements community, we should be also doing that. And we are already doing that. And what's the evidence? This is NAPA's Road Forward document that was released, I think, about a couple of months ago. And if you see that, there are different sections. And one of the sections says, promote the use of WMA technology to reduce temperatures and emissions during asphalt mixture production, quantify upstream impacts of additive production, blah, all of that. I'm not going to spend time reading that. But NAPA also outlined its objective that by 2050, it will try to achieve net zero carbon emissions in the asphalt production and paving industry, right? So it's obvious that the need of the time is towards sustainable alternatives, and warm mix asphalt has been identified as one of the sustainable alternatives. So my talk is along these lines on something that we are doing here at for ODOT, for Oklahoma Department of Transportation. I'll talk about the project in a little bit. So my presentation outline is warm mix asphalt, why and what is it and why do we care about it, binder properties, mixture properties, and life cycle assessment, which is basically an indicator of sustainability, and what are the challenges we are facing and path forward. Okay, I'll present some of our lab test results. I will probably go through that fairly quickly because of technology issues. This webinar kind of got pushed back, and so we'll see how that goes. Okay, so I always start my presentations with acknowledgements because I don't want to ever rush at the end of my presentation and spend less time thanking the people who make these things happen. First of all, this is a collaborative project between Oklahoma State and Texas Transportation Institute. So my good friend Fuji Zhao and our postdoc Runhua Zhang, they are doing all the binder testing right there. Every binder data that I'm going to present right now is being tested at TTI, and we are jointly analyzing the data. Aishan Moshfeghi is my graduate student, PhD student. She's doing all the data analysis work. Kevin Suter was the previous asphalt program manager at ODOT, and David Vivanco is the current one. ODOT Research Office. Ingevity, Richard Steger, Dennis Muncy, Jason Bossano, and Ryan Brown, they have been great partners in this project, and we are working together on a lot of things. And every other industry partner that has contributed materials as well as OAPA for their support, the Oklahoma Asphalt Pavement Association. Okay, so the what and why, right? So why do we even care about it? And this is a group of asphalt experts. I'm probably preaching to the choir, but you know what we want? We need our binder to be stiff enough at higher temperatures so that it's not rutting and stuff. It should be soft enough at low and intermediate temperatures so that we do not have a lot of fatigue cracking at intermediate temperatures, thermal cracking at low temperatures and stuff. But what happens to binder when we heat it to very high temperatures? We lose the lighter components, which is basically the maltines, and we expedite the oxidation. So isn't it obvious that if we could achieve everything that we achieve by heating the asphalt to a very high temperature, if we can achieve it at a lower temperature, of course, yes, I am aware of the aggregate drying, aggregate moisture removal and everything. So we'll get to that, okay? But the whole idea, if we achieve that, isn't it better, or is it better, right? So let's take a look at it. So first of all, this is a webinar on warm mix asphalt, and the interesting thing is that there is not one single definition of what warm mix asphalt is. Okay, so a Newcomb in 2006, he kind of presented a generic, he says like 68 to 120 Fahrenheit, 280 to 340 Fahrenheit, and then 220 to 275 Fahrenheit. So basically warm mix asphalt was 220 to 275 Fahrenheit. But then there are other definitions as well. So Newcomb himself says 30 to 100 Fahrenheit lower than HMA is your warm mix. D'Angelo said 35 to 55 Celsius lower than HMA. West et al. Said 25 Fahrenheit lower than HMA to all the way going down to the boiling point of water. FHWA on their warm mix asphalt website, they define it 30 to 120 F lower than the traditional hot mix. So basically, there are a lot of definitions. So what is warm, right? If you go to the industry or go to the experts, and they will actually say that anything lower than 300 Fahrenheit, maybe we're going to talk about that as warm, maybe 275 and stuff like that. So I want to tell you that here, it's actually the industry itself has not agreed on a single definition. Okay, advantages, the previous two presentations, they have talked a lot about it. There's reduced fuel consumption, greenhouse gas emissions, reduced mixture aging, improved cracking resistance, all the way to decreased dust production and stuff like that. I mean, this is full in the literature, so I'm not going to spend a lot of time on this. Okay, So what happens during aging? We all know there is short-term aging, there is long-term aging. So when we are doing a warm mix, and when I say warm mix, I want to refer to true warm mix, okay? Because we all know, if we have worked with, contractors, DOTs and stuff like that, and the current practice, a lot of times in projects, we do add a chemical additive or warm mix additive, but that is not really reducing the temperature. In this project, we are talking about actually reducing the temperature. Okay, so warm mix actually means reducing the temperature, which basically means it will reduce your short-term aging temperature, which actually is reflected through the Rpfo aging. And Dr. Hussein's last slide was actually a really nice lead into this presentation, because in this study, we do look at reduced Rpfo temperatures and multiple cycles of PAV and everything. Okay, and this is actually a very simple plot, actually by Ingevity. And if you see that as the temperature increases, Rtfo conditioning temperature, the mass loss in the binder increases significantly. So we are losing more and more maltines, we are losing the parts. And is that actually hurting us a lot? Can we actually, if in our warm mix technology, and in this project, we're looking at chemical warm mix, if we can actually preserve some of those materials, we can prevent that loss. Are we going to gain a lot, or what are we going to gain? Right? So this is the history of WMA. For the sake of time, I'm going to skip this. Different types, again, it has been presented in the previous two presentations. In this project, we are only looking at liquid chemical additives. Okay, and just to see how much warm mix is used in Oklahoma. This is year-by-year data by Kevin Suter in a presentation in 2021, and if you see, about 2015, there was a peak that about 57.9% of all the mixtures in Oklahoma had chemical warm mix. Had warm mix asphalt was produced. So not necessarily reduced temperature, but either a chemical additive was worked or some kind of foaming was used and stuff like that. Okay, in 2020, it is a little less than that. It's about 37.2%. I honestly don't know the reason for that. But remember, this is warm mix additive usage and some foaming and stuff. This is not this does not reflect reduced temperature. There is hardly any very, very minimal stuff where actually reduced temperature happens. Okay, so in our project, we are looking at chemical warm mix, and chemical warm mix is added as an additive to the bitumen. Or used as emulsion, and it basically tries to reduces the production and compaction temperature and internal friction between asphalt and aggregate. So what are the research questions that we are trying to answer here? So what are the benefits of actually producing warm? Remember, we are focusing on the reduced temperature here. And when we say that 57% is warm mix asphalt produced and stuff, are we really taking benefit of what this warm mix technology can do for us? Are we actually leveraging it properly? How can chemical WMA be integrated into balanced mix design framework? Every state or a lot of states are now moving into performance-based mix design or balanced mix design and stuff. How do we do that? Do we really just do a BMD and then just add WMA to it? The answer is no. There has to be a systematic integration into it. And does it actually align well with the constant search for sustainable construction practices? Right. So this is our project. It started in January 2021, and it's a collaboration between Oklahoma State and Dr. Fuji Zhao. And Runhua Zhang is a postdoc. Aishan is a grad student. ODOT is, of course, thank you to ODOT for the sponsoring of this. And Ingevity is a partner to us, and so are several other producers. Okay, so what are we doing there? Here, we are actually testing 4 different types of binders. We are testing 3 PG64-22 and 1 76-28. We're talking about 2 different mix types. One is a 12.5 millimeter, one is a 19 millimeter. These are the 2 most used mixer types. We're looking at 4 different chemical WMA vendors. So we selected them, and we are intentionally in our representations and stuff, we are actually anonymizing the vendors and stuff. We'll list who are they, and we are intentionally anonymizing because we don't want to introduce any bias in our analysis. And we are going to look at binder properties, then mixed properties, then we're going to do pavement performance prediction using Pavement Wmi design, and we're going to do LCA and LCCA to see how it is actually going to be beneficial in the long term. As of course, as you can imagine, we are not going to be able to do all materials for all tests, so it's going to be a statistical mixed design, experimental design. We're going to look at the rutting parameter, delta TC, Glover row parameter. For the mix, we are looking at rutting, ideal CT, ideal RT, which can be a production time quick rutting rapid rutting test that was recently developed. We're doing dynamic modulus and cyclic fatigue as well for inputs into our pavement ME design and FlexPave work. Example, performance quantification index. We're basically saying that what is a certain characteristic for a BMD WMA mixture divided by what would be for a regular rutting HMA mixture, and we're going to identify the benefits. Okay, and we're going to do long-term performance. We're going to work with ODOT to collect data for our NCAT sections as well as the SPS 10 sections and see how they are performing with time. This project per se, because of its duration, it doesn't have any construction and monitoring. However, we are working with contractors to actually produce mixes at lower temperature. This construction season, we are going to be batching those mixes or collecting samples, and we're going to be testing them in the lab as well. Ultimately, we're going to produce a specification, and we are also doing some supplemental work along the lines of the sustainability thing that I just mentioned about. This is not originally part of this project, but my team at OSU, we're actually working on in parallel and collaborating with ODOT to actually carry out LCA, life cycle assessment of some of the mixes, including some of the war mix asphalt mixes. Of course, there are challenges. That's a talk by itself, and unfortunately, I will not have time to talk about all of that. So just quickly think, reduced Rpfo temperature. Some of you may have seen some work by Ingevity back in 2020, where the temperatures were reduced for typical binders, where here I'm presenting data for one of our binders, and this is a 64 minus 22. We actually did the Rpfo at the regular 163, as well as a reduced temperature of 135. Okay, now somebody will say, what is 135? Is 135 actually reflecting your WMA actual mixture? That is a very, very good question. If you convert 135, it actually becomes 275 Fahrenheit, right? So that's kind of a typical definition of a war mix asphalt. But if somebody is producing at 295, or so, which is still below 300 and still technically is like a war mix and stuff, is that actually meeting this criteria? The answer is we don't know yet. We are doing this at different temperatures, and we will find out what's going on. So as you can see that in the initial aging, there is a big gap, and that gap kind of stays parallel as you increase PAV aging. For this binder, we went into 2 cycles of PAV. For the next binder, which is a 76 minus 28, we went into 3 cycles of PAV, okay, at different Rtfo temperatures. And we are seeing that the lines are pretty much parallel during PAV. Of course, there is a little bit deviation happening here, but the biggest difference happens at the Rtfo temperature. In other words, the stiffening of the binder is happening mostly during the short-term aging, during the production. If we reduce temperature, we will probably be benefiting significantly based on that, right? This is another way of presenting the data. This is regarding non-load related cracking using the Glover row parameter. And this is from the literature. Actually, this is Ingevity's data, where what they did is they actually tried different temperatures, Rtfo temperatures, and at different PAV cycles, they tracked how the Glover row parameter value was increasing, or in the y-axis, if you see, it's called percent remaining Glover row parameter. In other words, the way the Glover row parameter was defined is that at 180 kilopascal, once you go beyond that, it's like a crack warning. And once you go beyond 600, that's the cracking limit. That's when cracking happens. So 0% life remains at 600 kPa. So we have done similar work. This is our PG64 minus 28 minus 22 material. And there is a chemical war mix additive number 1. Intentionally, the name has been removed. But if you look at it, the reduced temperature, Rtfo temperature 135, it actually takes it takes almost 40 hours, like 2 PAV cycles, to actually go to the 600 kPa warning. In other words, the deterioration of the Glover row parameter, which is non-load related cracking performance, it actually is slower when you oxidize it to a lower temperature or short-term age to a lower temperature. Similar stuff, this is for a 76 minus 28. A lot of data here, and based on what Daniel told me, he would still want to end quickly. So I'm going to just stop, not go into a lot of details, but look at this. 149 Celsius we are doing here, and look at with chemical war mix additive number 2, and look how slow the deterioration in this life is. And we have gone into 3 PAV cycles, and still the Glover-Rowe parameter is not showing that it is actually even beyond the 180 kPa. So this additive is helping significantly. Remember, our objective in this project is not to promote one material over the other, or in fact, that's the objective of this webinar. We are basically talking about the whole war mix asphalt technology, and it's really working well. This is another way of doing this. This is called black space diagrams. Again, G star over phase angle against phase angle, and there are zones where the material lies. And if you look at it at Rpfo 135, this material lies at no block cracking zone. And this I'm going to just show this one plot, and then we'll try to summarize and whatnot. So, but if you look at it, here is what's happening. As you keep oxidizing the material, you start moving up and up and up and up. And see, if you oxidize, if you Rtfo age it at 163 and then 40 hours of PAV, now you are finally in the range of block cracking. This is one of the materials. This is the so this line. These plots are for 64 minus 22, and these points are all for 76 minus 28. And we are doing multiple different conditions. So just from the table, this is original binder, Rtfo at 135, Rtfo at 163. Then after 135, you do PAV 20. After 163, you do PAV 20. After 135, you do PAV 40. And after 163, you do PAV 40. Similarly, for this one, you have 149, which is 76 minus 28. Of course, for such a stiff binder, you really don't do 135. That's not going to help you at all. So we do 149, 163, 177. And after that, we do PAV 20, 40, and 60. We're going 3 cycles of PAV. And this is the data, but I'm going to skip over it for now. This is another way of analyzing for R value, which is proposed by Christensen. And actually it said that, with aging, the R value should increase, and the crossover frequency, which is where the G star and G double star, the lines, they basically G prime and G double prime lines, they basically cross and stuff, which is 45-degree phase angle. The crossover frequency will decrease. And for unmodified 64 minus 22, we see that trend. For modified, which is chemical additive modified, we see the same trend. But when we go to a very highly polymer modified material, that trend is not visible. So that's basically what means is that these traditional R value based analysis and stuff is not going to work based on these polymer modified materials, because the crossover frequency for the polymer may actually be different from the binder itself, right? So there is a lot of analysis going on. We're actually working on a paper based on some of that analysis. I'm going to skip over this. So right now we're just working on the binder test. We're 1 year into the project. The mixture test is going to start sometime later this summer. We are going to work on mixing as in the lab, as well as collecting field mix plant mix samples, and then we're actually looking at the entire balanced mix design framework and trying to incorporate that. Finally, I'll end with a little bit on life cycle assessment. We want to present, or we want to analyze, because of the move or because the demand of the time, we want to see whether from an LCA point of view, the war mix asphalt actually does make sense or not, right? So traditionally, it has been function, cost, and safety. But now for sustainable engineering, we need to look at impact on the planet and impact on society. But right now, society LCA is not kind of somewhere we are yet, but on the environment, at least, there is EPDs are starting, environmental product declarations are starting to be produced. The NAPA has several of them on their website. Several DOTs have started requiring, and that's the way to go. And federal procurement will require that very soon, and we are going to require some of that. This is a plot. Actually, Dr. Mohammed showed a version of this in his presentation, so I'm going to move from that. But the EPDs, the environmental product declarations, right now, they actually go from a cradle to gate. So they don't actually consider how beneficial these war mix technologies are in the field, how we are actually extending the pavement life as well. And we need to consider that, because that is where we are actually going to get a lot of benefit from these technologies. Okay. There was a study NCHRP, there was some challenges, there was lack of contractor set, there was lack of support for WMA implementation, it was a cost of WMA technology or equipment, a lack of understanding. This is what they thought was challenges in front of implementing, but they also proposed some recommendations. And one of the recommendations is actually provide incentives. And actually, the Oklahoma Asphalt Pavement Association is actually considering some of these, is if we can, or they can actually implement an incentive for producers to actually produce mixes at a lower temperature and use war mix technology, because it's going to be beneficial for all of them. And that is what we are hoping to achieve with this project. And we are only 1 year into it. This is an overview, and there is a lot to be done. So in summary, several projects and literature and our data has actually shown binder properties are improving significantly. Mixed properties, literature has shown, we haven't tested it yet, but that's what the beneficial is. The other presenters, actually, Dr. Muhammad showed the field condition as well, the field performance as well, and we will be looking at some of the sections in Oklahoma as well. And we need to consider how the effect of aging is actually quantified for unmodified versus polymer modified binders. That's a big difference. It's not going to be one hat fits all kind of thing. And we need to find a way how to accurately or properly incorporate WMA into balance mix design. It's not just that you do a conventional BMD and just add WMA, because that doesn't really make sense in terms of anything. So that's basically what it is. This is Dr. Zhao and Runhua from TTI. I don't think they were able to attend today. And Aishan, my student. And we probably are out of time, but anybody wants to email me any questions or anything, this is my contact information, and I will be very happy to answer everything. And finally, thanks to ODOT for the support and all our industry partners for this work. Thank you very much.
Thank you very much, Dr. Mishra. That was really great. Okay, just 1 second. So this concludes the presentation portion of our webinar. Now we will start receiving questions from the attendees. We already have some on the chat. We're going to start with those.
Daniel, can I start my question?
Yeah, of course.
Okay, so my first questions are to Dr. Loai. So Dr. Loai, can you share your screen, please, and get the slide where you were discussing or showing the 4 test sections that you included in your study?
Okay, just start sharing.
So Dr. Loai, can you hear me? Okay, so I think Dr. Loai cannot hear. So Daniel, can you read the questions for Dr. Zahid and Dr. Mishra? I can see that there are 2 questions.
Okay, I'm trying to get the file up, Mohammed.
Okay.
Yeah.
Okay. That's what you wanted to see?
Yeah, that one. So my question is, first, thank you for your research and for these exciting results. My question is, when you looked at, let's say, LA 3121, did you look at the pavement condition index or for the NDC's indicators before the application of that rehabilitation treatment? Because I assume that this is in a field testing, so I can see that the length of each section, you have 2.3 mile and 1.5 mile. So let's talk about the 2.3 mile, for example. I assume that the pavement condition index between the different sections was not the same. I mean, before the application of the treatment, which will affect the performance. So did you check whether this is?
Yeah, that was the same. Actually, it's available.
Okay.
The objective of this thing is just, for the interest of time, I just presented the snapshot of what is it at time 8. So all these projects, they had a PCI level where it triggered an action. And this particular section, it is consecutive. So they were all in a pavement section where they had no exits. So we want to make sure that traffic levels are similar. And they were all on the same lane. So the answer to your question is that they all have similar PCI or conditions because they had to be milled. And 3121, for example, it was milled and then it was overlaid. It's mill and fill, basically.
Okay, and then all the values of the indices that you have presented, they were after how many years after the construction? So what was the pavement age when you collected these indices? I may have missed this.
Okay, see that slide? It says 8 years. You see what the slide is?
8 years. Oh. So my following question, and this is the last question, did you look at the deterioration of the PCI to compare the service life of the WMA and the conventional? Because I'm just assuming that there might be just a difference if you looked at the service life or at the deterioration of the PCI.
What do you mean deterioration? Do you mean over time? From
Yeah,
time
exactly. So if you look over 20 years and you looked at the PCI when it
the project is just 8 years old. I mean, this project is new. I mean, we're not there yet.
Okay.
We haven't got to 20 years.
Okay, because I think that would be exciting. Even, I mean,
well, that's the purpose of this project, is that we're continuing to monitor the performance. And at the time when they were collected, this is, I believe it was 2019, those data. And at the 2019, they were, these are the ages for them.
Okay. Yeah, it would be exciting to look in the future about how the PCI differs over the years between the WMA and that control sections.
Well, that's the whole idea. See, the whole idea is that you hear a lot of things and all this lab work and all these things, but the end of the day is that how did it do in the field so that we can convince policymakers that, yes, it does work, whatever variation that one has to allocate.
Okay, thank you very much, Dr. Lai.
Welcome.
Perfect. Okay, from the chat, we have one question for Dr. Mohammed. So when comparing the indices between the regular WMA asphalt and asphalt sections with RAP, you have looked at the final index at time of collection, right?
Yes, sorry, because the title says field performance, long-term field performance, which basically state that at that time of 8 years. Do we have them at year 6 and year 8? The answer is yes. And it's certainly, there is a rate of change, but for the scope of this work at the moment is that I want to know what is it right now, basically.
Okay, this question continues. It says, were you able to see the history of these indices degradation from PMS data over the years and compare between the pavement types?
Yeah, that's what I just said. It's
yeah, I think that's similar to my question.
Okay, okay, yeah.
That's what the end of the day, you know, what you're asking me is that, did we collect them at year 6? Did we collect them at year 4? Did we collect them at year 2? And yes, they are available. But the purpose of this work is that, how did it do right now? Yes, it did deteriorate over time.
Okay. Now I'm seeing a question for Dr. Hossein from Elise Mansour also. Can you please elaborate about the gassing oven used for the performance testing? Is it within the binary performance requirements test at Arkansas?
Okay, so the question question is the purpose of having the degassing oven?
Yeah, about the degassing oven.
Okay. Yeah. So there is, I forgot like exact procedure. There is a standard to degas the binder. That is actually like once you do the PABasing, basically you are injecting air in there. So there are a lot of air bubbles, and you need to take the air out. Otherwise, what will happen? There will be a lot of these bubbles inside the BBR sample that you are going to. So I believe like it is, yeah, we did it high temperature. It is, yeah, it is from ATS. They have the device and 170 degrees Celsius or 120 at that temperature. Where is it? Probably 120 degrees Celsius temperature. So you have like put a kind of canister of asphalt binder. You can put like the device that we have. You can put, I believe, like 3 or 4. So you can put those, and then after a certain time, you will see that it applies suction and temperature and suction, and then takes the bubble air out. And at the end, you will see not much air is coming out. Otherwise, the beam that you are going to make, that will have a lot of like bubble coming out, and that will not be good beam sample. So that is like Astro standard out there for that. It's not like those 6 super pave test, but that is another kind of like how you take the air out from there.
Yeah, so I can add to this. At least it's
Did I
not
answer the
an
question?
Arkansas test. It is a standard test that many agencies uses. Some of them chooses not to for time, basically.
Yes, thank you, doctor. Like, because this test, I was not familiar with it. This is why I was wondering if it is a requirement, but it seems like it is needed to remove the air bubbles, as you just mentioned, doctor.
Yes.
Thank you.
Thank you, Dr. Mohammed.
Okay, we have a question for Dr. Mishra. It says, so do you also think that warm mix temperature ranges should differ between climatic zones?
I don't know if I actually understand the question. I don't know if she's talking about the definition, like how I said there are multiple definitions, or they're actually talking about at what temperature warm mix should be produced. But so I'll try to answer both ways. Like, you know, the production temperature is not really affected by climate, right? I mean, it is the production temperature is essentially why is the temperature at a certain range? Because we need to remove all the moisture from the aggregates. We need to heat the aggregates. We need to make the asphalt liquid. We need to make that coating, and that's it. That's all we need. That is the whole purpose of production temperature, right? So it doesn't really matter regarding climatic zones. Like if like, let's just say hypothetically speaking, we somehow magically find a chemical or something that actually does all of these jobs, and you know, of course the water from the aggregates need to go away and everything, but still everything we get and proper coating happens and everything at a significantly, like a temperature reduced by 200 Fahrenheit. I mean, why not, right? So I think if that's the question, then my answer is no. I mean, as long as we are able to achieve adequate coating and mixing and workability and everything, that's it. That should be the factors that govern production temperature.
Okay. Okay, we have a new question for Dr. Hussain from Vikas Kumar. It says, what parameter did you use for measuring percentage retention in the Buoying test?
Oh, there is a Texas boiling test. There is a they have their own test technique. So there is a designation. Texas DOT came up with that standard. Not an Astro, but that's the Texas. It's not called as Texas boiling test. And so basically, visually looking into like how much the asphalt is retained after the boiling test, and more retaining, so that is kind of a better. So you do the ranking based on your visual inspection. like 20%, 30%, 40, 50, 60, like that way, visually inspected. There is no kind of like microscope or anything.
Perfect.
I have one final question to Dr. Loai. Dr. Loai, when you were looking at the
You have
indices,
limited the question to me, you know that, right? You can't ask too many questions.
I mean, if you don't want that question, but that I really
Okay,
want
go ahead. No, just
real
go
answer
ahead.
for that question.
Go
Yeah.
ahead.
When you were looking at the indices, did you take, because each section was about 2 miles, so did you take the average for the indices, or
Yes.
did you consider the difference or the?
No, we looked at the
standard
average,
deviation?
and a lot of times, you know, it's a very tedious process, and because we want to make sure that these are reflective of load related, because sometimes they were patching, and you don't want to include, for example, patching. It is because sometimes a utility work has been done on the section. And when you look at the index by itself, then you see a variation or something happen, or sometimes it improves. And so we actually had the student kind of, you know, drive the, you know, if you're familiar with our PMS, you know, with the vision, iVision, we had him drive the route and look at every section, mark it out. And if there are anything other than what we expect to see, then we will mark it out, and that's part of the process and the data mining analysis.
Okay, perfect. Thank you.
Okay. Do we have any other questions? Let's wait a second to see if we have any other questions.
So Dr. Zahid, because I may have also made that, did you use the aggregates that you included in your presentation? So did you have any asphalt mixtures?
No, we did not have any asphalt mixture other than with there, and then did the Texas boiling there. That is the only mixture test that we did.
Okay.
Okay. I think we're done with the question. So again, I would like to thank our presenters for the time and technical presentations. I also want to thank the attendees. Please let me know if you have any questions about the webinar series and about Tran-SET. Otherwise, have a great rest of your day.
Thank you.